Hello, ARRL members and QST readers worldwide. My name is Dave Kassler, amateur call sign KE0OG, and I write the Ask Dave column in QST. This is the video supplement that comes along with the February 2025 edition, and we're going to talk a little bit about the ionosphere. In the article, we talked about what a lot of people see on their waterfalls when they are hearing the ionospheric sounder. What we're going to talk about here is what the ionospheric sounder does with the information that it receives. This is Ask Dave from February 2025, and this first article here is about what I call the diagonal on the waterfall. And down here, you can see this little diagonal line right here. That's an ionospheric sounder. It's a radar pointed straight up at the ionosphere, and it's changing frequency. Remember, in here, frequency, lowest frequencies here, highest frequencies here. Most recent time is here, longest time is here. So this is what we usually use to see signals, but this one is changing in frequency as it goes up. Now, I did a very thorough video on this a couple years ago. It's Ask Dave 385, where we talk about a whole lot more about some of the discoveries in the ionosphere and so on. So take a look at that. Now, let's take a look, instead of what we see in the waterfall, what the ionospheric sounder is actually coming up with. Okay, now, this is from Wikipedia, and here is what it says about that. This ionosphere shows a well-formed F layer. That's this right here, okay, this, with a peak ionization of around 220 kilometers, which is about right there. See, there's the well-formed F layer. There's also a less obvious E layer at an altitude of about 110 kilometers. That's this little bit right here. See where it curves around to the side. The ionogram clearly shows how the transmitted Digison signal splits into the reflected ordinary and extraordinary waves. Now, this is the ordinary wave, this pink one. This is the extraordinary wave. You'll recall from the ARRL book, if you've read this. If you haven't, I really recommend it. It's called Here to There, Radio Wave Propagation, and it talks about all of these different things like here. Fundamentally, when a wave hits the ionosphere, it splits into two. The ordinary wave is reflected. The extraordinary wave is also reflected, actually refracted, and sent back to the Earth. These two waves have opposite polarization. Each is circularly polarized, and note that they're different. They come off different parts of the ionosphere and so on. So the other thing that's interesting in this is that the parameter FOF2 right here, okay, is on the left side there, shows the highest frequency that will be reflected from the ionosphere for vertical incidence. Now, let's just take a look at this, okay? We've got a radar pointing straight up. It starts at 1 megahertz, goes to 10, so it's frequency this way. This is height of the ionosphere. It doesn't say kilometers, but I'm going to suspect it's kilometers, okay? Now, the thing fires straight up and listens. Then it changes frequency, fires straight up and listens, all right? Now, when you get up into here at 3 megahertz, it fires straight up and listens. Now, here's the thing. This will reflect the wave back down, and it will come back up and hit this thing again, and you can get a second time around. Now, when you have a radar that's doing that sort of thing, you see the real signal down here, and you see the second time around as though it's up here. There's nothing actually up here. It hits this, hit the ground, come up, hit it again, and come down. So we're looking at about 230. So that'd be about 460. And yep, there it is right there. Okay. So these are the second time around, or double hop frequencies. Okay. And what we see coming down here is, as the frequency comes up to here, this part right here is the part of the ionosphere that is refracting signals. Anything beyond this 5 megahertz right here is not refracted back, although the extraordinary wave is. So we look up here, the frequency for If it's shot straight up, the maximum frequency where you will get a response is just under 5 megahertz. Now this means that if we're wanting to do NVIS, which is straight up, straight down, near vertical incidence skywave propagation, the highest frequency we could use would be 80 meters, because the next higher band, 60 meters, is actually above this in frequency. Now note down here, you see this is a distance in kilometers, okay? The distance from where you are, right here, the maximum usable frequency for that distance starts out low, and as the thing refracts over a wider distance, it goes all the way up to 17.7. You could use 20 meters or possibly 17 and get out these long distances, okay? Now, during the day, these two lines will go over here to higher and so on, and they use the computer calculations to calculate. If you're going straight up, here's about the best you can do. If you want to go that far, use something in that range right there. Okay, that's getting real close to 40 meters. You could try that. Anything less than that would be the skip distance for 40 meters. Okay, so we've got a lot of things being done. This is the station at Gakona. The ionosondes are located around the world. They're all over everywhere. This happens to be a digital one, a digisonde, created by Lowell. Okay, and it's a digital radio. It's not very big, but it's extraordinarily expensive. They make very few of these. This is not like a commodity business where you can get all sorts of things for very low prices. These are extremely expensive, I think in the millions of dollars. And that's because each one is carefully and custom made and so on. Okay, so here's at the bottom, this is how to read one. The bottom is the frequency. You see that straight, and again, it goes straight up. So the straight up frequency here is just under 5 megahertz with a little bit on the extraordinary frequency. Now, the thing is that most of the energy that's refracted back is in the ordinary. Now, the ordinary and the extraordinary may look like they're in different frequencies. It actually has to do with how the ionosphere handles these signals. If you send up linearly polarized signals, such as from a dipole, something like that, when it hits the ionosphere, it's going to be split into two parts. And here you see the splitting taking down here. And these are circularly polarized in opposite senses. So most of it goes in the ordinary wave, and then the extraordinary wave. You can sometimes actually hear things on this signal, and you're not sure whether, because a linearly polarized antenna can pick up both left hand circularly polarized and right hand circularly polarized. Okay, but if you put up a circularly polarized antenna, it will hear either one of these depending on which way you have the handedness of the signal taken care of. Okay, this shows here at 2 megahertz, it's getting kind of constant things coming down. It's going up and getting a bunch of stuff back. This is hitting it at very low levels. This is the E layer giving into the F layer right here. Okay, the F1 layer and F2 layer during the daytime, and at night they combined, so you get something like this. Remember, this is the double hop. That does not mean there's anything up there. It hits this, bounces off the ground, hits it again, comes back, and it looks as though it went all the way up here for a single hop. This is a standard problem with ranges for radar. And this is a radar. It sends up and then listens for what comes back down. So now what you have is a little bit of understanding of what the people on the other end of the ionosonde are looking at. They're looking at this printout. There'll be something like this in some way, shape, or form, okay? And you can use these. All of these are publicly available from the organization that creates them, usually a university of some kind. And you can get the ones that are near you. You can get the ones that are going to be near where the collection is going to be if you're going overseas, and double, triple hops, etc. You can find out a lot of information from what these look like. So now you know, you see the both sides. You see on your waterfall that funny little diagonal line, and you see here what the scientists are actually getting out of it and how some of it is of great interest to ham radio operators, whether just for casual operating, DX, contesting, or whatever. So there you have it. So until we meet again for the March episode of the accompanying video, here's Dave, KE0OG 73.